You are listening to the Complete Developer Podcast, the podcast by coders, for coders, about all aspects of creating your best life as a developer.
I'm Will, the accomplished developer and aspiring software architect.
And I'm Beej, the advancing journeyman developer.
Complete Developer Podcast is supported by listeners like you. We are now on Patreon at www.patreon.com/Complete Developer Podcast.
Data, wherefore art thou, data? This week we're talking about primitive data types. We'll start with a brief introduction to data types, then delve into 5 basic primitive types.
I'm pretty sure I heard that one line that you just spoke on Star Trek at some point, like on the holodeck maybe.
Probably so. But before we get started, Will, what have you been fighting this week?
So, we're still trying to get a product out. We've got pretty much all the bugs wrapped up, except now we're trying to do final QA with our support department because they like to go through there and go, hey, these users are going to have problems with this, and this is going to cause a support issue, so we want to run stuff by them. And I'm waiting on that to get deployed and get tested and all that fun jazz. Of course, everybody was out with the Eclipse. And the other thing is we discovered that the audit trails, as they were coded initially, we haven't really looked at them in a while, and they were not sufficient.
I just saw a button on my new laptop, and I don't know what it does, so I'm curious as to if I should push it or not.
I wouldn't. It might be the power button. So yeah, we discovered that the way we were doing a lot of the audit trailing in the product it wasn't collecting enough data, for the full-on audit trail, like what they really wanted. And so I had to go back through and we're rewriting the triggers. And these are triggers on 30 different tables. Those tables have got a lot of fields, and we've got to record everything, what happened. And so I basically ended up writing a SQL script to write a SQL script. Yeah. I've been doing meta programming in SQL. It's exactly as bad as you think it is. You type for a while and then you stop and you just think, where did my life go wrong? How did I get here? And how do I not do this again? But, it's almost through. So yeah, other than the Eclipse, that's what I was doing today. So how about you?
Well, I'm still loving my new laptop. Recently discovered a button that opens up the gaming center. So I have a shortcut key for that.
And by recently, he means 35 seconds ago while we were recording. He's like, what's this do? Let's click on it, find out. Woo!
I had to say something else about it just to see your reaction. So, as you mentioned, it is Eclipse Day. I am wearing my official Eclipse t-shirt. If you guys saw the Facebook Live when we recorded this, you will have seen me wearing my official Eclipse t-shirt. I went down to my mom's place to work remote and watch the eclipse because she's got a couple of acres out in the middle of nowhere. So it was pretty nice. Not as out in the middle of nowhere as your parents, but still, it was nice. Quick update on my uncle. He is still in the hospital. Actually, since I wrote this part of the outline, I have learned that he has recovered enough to where they are going to be taking him tomorrow to a long-term facility for maybe a month or so to do intensive physical therapy to get his strength back up. So he's good enough to come out of the hospital. That's really awesome.
Yeah, that's a win.
He's still rather weak, but he is improving. I've been playing around with some new things to make our coding easier at work. I told my boss about one of them, AutoMapper, that you mentioned to me when I was asking about some other things, and got permission to do some research learning on the clock. So that's really cool.
Yeah.
Especially because right now we are sort of in that last minute. We're at the very end of the testers are just doing regression testing and making sure everything looks right, feels right, and stuff like that. But the developers are just supposed to sit by and be available. So I've been using this time to do some learning, which is really awesome. Speaking of clocks, though, I've got a project for when an alarm clock just isn't enough for IoTs. So let's go ahead and roll the music. This week for IoTs, I have a fun project for when an alarm clock just isn't enough to get your kids out of bed. It's called the Ejectabed. Not long ago, we talked about the Netduino coming back on the scene. I've kind of been looking at projects to play around with one. Do want to eventually buy one and build with it because you write the code in Visual Studio, so it's pretty awesome. I found this pretty fun idea for getting your kids out of bed when nothing else seems to work. It uses an old hospital bed, a servo, a Raspberry Pi 2B, and of course a Netduino to gently eject your kid from bed and get them going in the morning.
So I wonder what the QA process looks like.
Yeah.
I have concerns about, first of all, mains power, my soldering skills, the kid's bed, and a hospital bed of dubious provenance.
Well, you can check out the link in the show notes to find out more.
Yeah.
It's a pretty good tutorial. So
I mean, yeah, I like awards. I just don't like Darwin Awards.
So who's talking to us this week?
Well, this week we got a comment on the Code Kata episode from DA. So been listening for a while now. Some really good stuff. Wish more developers listen to you. Where do you get your Code Kata material?
I get a lot of stuff from codekata.org, codingwars.com, and codingdojo.com. I also create all the challenges for Dev Launchpad each month. I try to make them so that they can be used like a coding kata. Most of the time I get inspiration from various places, usually different interview questions I've had.
Yeah.
We'll base that because when I interviewed for the job that I have now, the whiteboard question I was given was actually a code kata that I'd been doing. And so I try to develop my code katas to be like whiteboard and coding challenge questions I've seen in the past.
Yeah, and I just kind of pull mine from experience more than anything. And usually the way that I do it is I try to combine 2 or 3 things that I'm trying to learn at the same time in a small way.
I know one thing I'll do if I'm trying to, well, when you were showing me some of the shortcut keys in Visual Studio, when I really wanted to get those down, I picked a code kata I'd done before.
Yeah, and you just hammer it so that you get better at your IDE skills.
Exactly. Yeah. But we want to say thanks for the comment. We really appreciate the feedback. Send us an email to nickbeards@CompleteDeveloperPodcast.com with your contact information because we've got a Complete Developer water bottle just for you. And guys, if you'd like your very own Complete Developer water bottle, leave us a review on iTunes or comment on the website or any of our social media. We post all our episodes to Facebook, LinkedIn, Twitter, Google+. We're also on Path and Tumblr. Do you guys want to come out and meet us? And Will, what are you talking about down in Huntsville, Alabama?
I am going to be talking about why your DBA hates your ORM.
Didn't we have an episode about that?
We did.
Yeah.
And, not only are the things from that episode in the mix, but a lot of other stuff that I didn't think about. Mm-hmm. And a lot of things that I've encountered, since that was kind of on my mind. Yeah. Since that episode has come out, stuff that I've run into in the job. So kind of trying to get that together and to show developers maybe a better way to work with your DBA so that you address their concerns. Instead of having them go, no, you can't use EF, you have to use ADO.NET because EF causes problems for them. So I think it'd be pretty good material.
That's awesome. Well, that's going to be down in Huntsville, Alabama on October 13th and 14th at the DevSpace Conference. This is North Alabama's premier polyglot technology conference. And in addition to hearing Will speak, you can also come down and meet the two of us. We'll also have some of the other people that we've had on the show visiting the booth as well. But tickets are on sale now. And to get 10% off, use the code COMPLETEDEV or follow the link in the show notes. Again, that's DevSpace in Huntsville, Alabama on October 13th and 14th. Generally speaking, a data type is either primitive or composite. A primitive data type can either be a basic type that provides kind of the basic building blocks for a language, or a built-in type that the language treats and supports as a basic type. Composite types are ones that are a combination of either primitive types or other composite types. These may or may not be built into the language you're using. The real difference between the two is that primitive types, like prime numbers, cannot be decomposed into smaller types.
And, I will add as well on this that, like types that are like a byte, you might think that could be decomposed into bits, but that's not what we're talking about here.
No.
It has to do with the way that it's laid out in memory.
No. In some places that you look, as in when I was doing the research for this episode, primitive data types mean anything that is built in to the language. However, that gets into language specifics, and we try to be as language agnostic as possible. So we're going to refer to the primitive types as the ones that cannot be broken down. And when we talk about composite types, they may be built in to the language or may be programmer defined.
Because, for instance, like a lot of languages will have a point type that's got an X and a Y. Well, it's obviously two integer values or two floats or two whatever. Yeah. And it's technically a composite, but it is built into the language.
Exactly. Now, most of your primitive types will be value types, meaning their value is a datum or specific set of bits. Therefore, a value type is the relationship between a set of data and a set of entities sharing the same attribute. Value types do not have a constraint on how the values are stored, so primitive types may not all have a direct relationship to objects in memory. In some languages, like C#, Swift, and others, the term value type refers to the way the value is assigned. When creating a value type, the full amount of memory used by that type is pooled. So if it's an int32, then 32 bits will be allocated for that variable. Value types are stored in the stack memory. If the value of a variable here changes, new memory isn't allocated as it's a fixed size. However, if you're copying that value to a new variable, it will create a new value in memory.
Right. And that tends to be pretty common with primitives, just because it makes it less hideous for things like multi-threaded operations and those sort of things.
Now, these are opposed to reference types, which point to a reference to the value. These types are not fixed in size, and therefore, if the value of a reference type changes, a new area of memory has to be allocated. However, if it is copied, then only the reference needs to be copied to the new variable. These are stored in the heap, but have a reference stored in the stack.
Right. So essentially what you're getting is a pointer, or something that they don't call a pointer necessarily, but it's kind of that. It's like instead of you getting a piece of paper, you get a piece of paper that says the paper's over there. is roughly how that works. And the reason that that's done that way is, you have large objects. You also have, if you have a managed heap, or you have some kind of heap allocation algorithm working, like you don't necessarily want to be messing with that.
Well, I know in languages like C#, this is how strings are treated.
Right. Strings, most objects, objects are typically treated.
I got a better understanding from our Let's Talk About Text episode when you were explaining how strings are treated by doing this research.
Right.
Like learning about the two different types. I'm like, I remember some of this from high school when I was learning computer science. Yeah. But it's been a long time ago. And so going through this and learning about it, it just it clicked, and I made that association on my own. And then I read where it said, this is how strings are treated in C#. I'm like, oh, yeah, that makes sense because I connected the dots basically between the two episodes.
Yeah. Now, C# strings are weird in the sense that they're immutable. So every string that has the same value is pointing at the same memory location, and they do stuff under the, it's basically a black box. The signal goes in and something comes out, and you really don't want to get into the middle of that.
We're going to talk a little bit about that later on in this episode. We'll actually get more into it when we get into the string data type, which is a composite type.
Right.
So on the episode where we talk about composite types, we'll get more detailed on that. Guys, there is a whole rabbit hole to go down on how data is stored, how it's copied, how it's manipulated in memory. There's a lot to learn here. And this started out as an episode on data structures, and I had to narrow it down to just primitive data types.
And you barely were able to fit that in.
Exactly. So we're going to have a few more episodes. I know we've already had some about numbers and strings and things like that, but we're going to continue to have episodes on different data types, especially as I learned more and I'm like, oh, I want to know more about this or about the lower level of this. We'll have more of those. We're also going to have more about just data types in general. So to start off, we're going to start with integers. An integer holds a mathematical integer up to a certain size. The range of numbers held in an integer, it's going to vary and depend on the byte or bit size of that type. This range scales exponentially as each bit added doubles the size of that range.
Right. And bear in mind, you get a block of 8 bits.
Yeah.
So it's, it goes 2 to the 8th.
Mm-hmm. The way this is described, and Will kind of hinted at it, is 2 raised to the power of the number of bits minus 1. And this is for unsigned integers, and we'll get into that in just a moment. Each bit represents a multiple of 2. It's an on-off. 8-bit, you can have numbers up to 2 to the power of 8 minus 1. And can you tell us why we have that minus 1?
Because 0.
Exactly.
Because we start counting at 0 in computer programming.
Yeah. And so with that, 2 raised to the power of 8 minus 1, we can have from 0 to 255.
And if you have a word, in other words, a 16-bit value, then it's 2 to the 16th minus 1, which is 65,535.
Yeah, and that's as high as you can count with that.
With that many bits.
Now,
in an integer.
In an integer, yes. These may be signed or unsigned. If they are signed, the first bit in the sequence will be associated with the sign of the integer, positive or negative. The range...
Which is also why sometimes you'll get weird overflow errors.
Yeah.
Where something like it looks like it's going up and then all of a sudden it's negative. And, those kind of things. It's because it's overflowed into the sign bit and they weren't checking properly.
Yeah. I can see that.
Yeah.
Very low level thing, but in some of the Delphi you do, I can totally see that.
Or like old Nintendo games and those kind of things. You remember like in, I think it did it in Mario Brothers 3. Like there's a thing where you could like jump on the Koopa and like kick it and it would bounce back and forth and the little bullet things would hit it. And it would keep, as you got the hits, it would keep raising up and then you would get 1-ups. Well, eventually you could make that overflow and it would display as a negative, if I remember correctly. It was one of the Mario Brothers games. But like that's a very real thing.
It was the first Super Mario Brothers or the second?
It was either the first one or the third one because I hated the second one.
Yeah.
So it wasn't the second one because I beat it exactly once and then it's on the shelf.
Nice. Yeah. These are going to range between the lowest negative and the highest positive number with 0 as the median. And you're going to have one more negative than positive because that's where they take off the minus 1 for the 0.
Yeah, it's got to fall on one side or the other.
Yeah. So it'll be, instead of 2 raised to the number of bits minus 1, the range is going to be negative 2 to the number of bits minus 1.
Yeah, it's negative parentheses.
So in a 16-bit system, because you have to take 1 bit for the sign, it would be 2 to the 15th. It would be negative 2 to the 15th, and this is confusing. Look at the show notes, guys, because it'll make a lot more sense there. It'll be negative 2 to the 15th up to 2 to the 15th minus 1.
Right. And you can just look at it as if you took that full unsigned size and you shifted it where 0 was in the middle. Well, it had to be slightly off because of the available size, but give or take, that's what's happening spatially.
It's a good description.
Yeah. I mean, it was kind of the way they described it in class.
So just a couple examples. An 8-bit signed range is negative 2 to the 7th to 2 to the 7th minus 1, or negative 128 up to 127.
Right.
And I've already described a 16-bit range as negative 2 to the 15th up to 2 to the 15th minus 1, or negative 32,768 up to 32,767.
And I'm sure there's a few people whose eyes are now glazing over from all these numbers.
Don't worry, it gets worse.
Yeah.
Unsigned integers are treated as always positive.
Right. Which is why it's real important to know which one you're dealing with.
Exactly.
Passing stuff back and forth, because you could give something a unsigned integer that is large and it goes, hey, this is negative.
I could see that being a big problem.
Yeah.
Wow, yeah.
Yeah. Like think of mileage calculations.
Yeah. So the reason I could see that being a big problem is the memory states for these are reversed for the negatives on signed integers. So 0 as the sign, so it's positive, and then all zeros is 0.
Right.
But 1 for the sign, meaning it's negative, and all zeros is negative 128. And then the opposite, 0 for the sign, it's positive, all ones is 127, and 1 as the negative, all ones is negative 0.
Yeah, it's really hard. I'm not an auditory learner. I'm sorry.
Yeah, guys, go look at the show notes on this one because it's going to make a lot more sense.
And here's the thing too, like you don't really have to know this. Just check your crap. Because
most people are never going to really get into this because this is very low level.
Yeah.
If you're possibly doing some IoT stuff, you might get into it.
Or you're interacting with like old school APIs, those kind of things.
Interacting with older systems. You're doing things with like IoT devices or wearables where you actually have to worry about the memory.
Right.
Then you might get into this. Otherwise, you're probably never going to see it. And this is just a matter of, hey, it's a cool thing to know.
Right.
So typically, integer literals are written as regular numerals with a sequence of digits. And if it is negative, a minus sign is out in front.
And most languages will go with that because that's kind of the way we all do it. Now, there are some weird things that can happen. You can't do digit grouping, like with commas and the like, in most languages. There are some exceptions to that, where they've added that. I want to say VB.net has done that recently.
Do they add commas, or is it like, I saw one where there was underscores.
I think it was underscores maybe, and that was
one
bits.
with spaces.
Yeah, and it was like for binary.
Yeah.
Now, you can't express it in different bases. This will burn you in JavaScript.
Mm-hmm.
When you get something that comes out, some environments you'll get it has a leading 0. They go, oh, it must be octal, because that seems like a good leap of faith. Let's take that one. So you'll see stuff like when you're writing code in a particular language where they have basically string literals for numeric values, and then the compiler translates it and goes on with life. And those will vary a little bit. They don't vary much because that's pretty much the first thing we were doing with computers. And so that's kind of baked in so early that we don't have to worry about it. Now, floating point numbers are horrible. This is such a pain point for a lot of developers. You'll go along for a little while and you'll think you're okay, and then it hits you again. So just if you think you got it, just wait for the next round of it.
Oh, trust me, this is the part that took me the longest to write, and you'd already done an episode on them.
Yeah.
If that says anything, guys.
Yeah, it's nasty, right? Because you're essentially storing a was it called the decimal and the mantissa, which is basically, hey, here's the part before the period and the part after the period. Sorta.
All right, so let's get into it. The floating point numbers are rational numbers that may have a decimal or fractional part. They are not actually the real numbers, but representations that are stored as a formula. And the term floating point refers to the fact that the decimal point or radix point or binary point, there's a lot of different terms for that same.
That's why you call it the period, because everybody knows what that is.
Yeah. That can be placed anywhere relative to the significant digits. These are usually stored in a variation of scientific notation. For example, the literal for a floating point typically has a decimal and a lowercase or uppercase e to show scientific notation. So 6.022 E23 represents 6.022 times 10 to the 23rd, the number that always makes me crave guacamole.
Is that Avogadro's constant?
Yes.
Okay. Wow. Okay, so Avogadro's constant makes you crave guacamole. Okay, okay. It took me a minute. I guess I get it. Yeah, and
okay, guys, let me just put it this way. I wrote that joke working on this part of the outline. That's how bad this was.
Yeah. Yeah, and I haven't seen it represented that way very often.
Mm-hmm.
Because I don't even know if you can do it that way in C# or not.
It outputs that way sometimes.
I've seen it output that way. I just haven't seen it input.
Yeah, no, I don't know if you can input it that way, but
then again, I wouldn't.
Yeah.
So, but anyway, the first number before the E is called the significand, and it determines the significance or precision of the number being represented.
And the E itself represents the base Typically, this is either base 2 binary or base 10 decimal, but it can be any number. Base 10 is easier for humans to understand and read. Base 2 is easier for computers to understand and read.
But some numbers can't be expressed
Exactly.
very easily without, picking a certain base, in that memory space. And that's the big thing with floating point is it's a very old compromise between storage considerations and what the machine could process and what you could put into it.
Mm-hmm. And the final number there is the exponent. And this is how many times the base is multiplied by itself. Hence 10 to the power of 23 in Avogadro's number. But as you said, some bases can't be used to represent certain numbers.
Right. Like, for instance, well, and you'll run into this anyway with irrational numbers. Mm-hmm. Just as an example that's easy for people to understand, expressing pi in base 10, you can't. Like, you can approximate pi to varying degrees of accuracy, but you're not going to hit it. Whereas if you express it in base pi, you can. And I think you'll probably have problems with expressing 10. Things
like 1/5 can't be expressed using binary.
Right.
It can in decimal or base 10.
Because there's not address space for that.
Exactly.
And there's no way, because it's going to overflow whatever you put it in. And this is a really weird thing to get your head around, that numbers aren't things, they represent things. And sometimes you can't represent those things in the base you're looking at them in. Mm-hmm. And with computers, you also have to look at the storage constraints and those kind of things. So typically these are formatted using IEEE 754 encoding, but that may differ based on the system you're using. I will state this, that's what the IEEE 754 encoding is what it says in the outline. I don't know that off the top of my head. You're not likely to need it either, but it's interesting if you want to go look at it.
I got that from your outline on numbers.
That's right. I know you did.
And then I went and looked it up.
Yeah. And you should totally do that. Just if you know it off the top of your head, okay, man. So the big thing with floating points is to understand that what you're trying to do is you're trying to express a number to an acceptable level of precision without overflowing the space that you have available.
That's a business definition.
Yeah. For instance, you may say, okay, I'm doing accounting and I need to be accurate to 100th of a cent. That's reasonable. Hey, that's, it's 4 decimal places. That's no big deal. Well, that's great. I'm flying a probe to Pluto. And I'm, for some reason I'm expressing things in meters because I'm crazy. Oh, that's right. I don't want to smash into the surface. So that's sort of important. I need a little more precision than 4 decimal places. Probably. Yeah. You're going to use larger floating point values.
You can always do like I do when I play Kerbal and just eyeball it the whole way down.
Yeah. Or just, just forget to convert from centimeters to inches. Just get that, because it makes a really glorious impact crater. And you deploy the parachute 30 feet after you hit the ground. It's great. We typically like to avoid that in computing because, those sort of mistakes are either expensive or they kill people. So it's better to avoid. So
I prefer landing on planets without an atmosphere. It's just a thing.
Yeah. I've played Kerbal. It's a good game. So single precision floating point numbers are 32-bit. And the first bit is reserved for the sign of the number, positive or negative. If it's floating point, typically you're going to always have a sign because you're trying to get a larger space of stuff, and it may go negative just because of the type of calculations you do. The next 8 bits are the exponent or the multiplier. And the final 23 bits are called the fraction, and that's where the significand is stored.
Double precision floating point numbers are 64-bit.
Right.
And like the single precision, the first bit is reserved for the sign. The next 11 bits are the exponent, and the final 52 bits are the fraction, where the significand is stored.
Yeah, and basically, you probably don't need to know these numbers exactly. Just know that, single precision floating point, it's got a smaller range that it can represent accurately.
What I've seen, at least in most of the C-based languages, is the single precision is float, and double precision is the double.
Right.
I don't know how that is in non-C-based languages or what they're called, because everything I looked up was either C# or Java, so...
Yeah.
And a little bit of, C++. Some of this stuff, when I was looking it up, there really wasn't much on C# to understand it. I had to go back to C++ to get low enough to understand what I was looking at.
Right. And if I remember correctly, Perl has got some pretty interesting constructs around all this stuff as well.
Oh, Perl has some craziness.
Yeah. Like every time I look at Perl stuff, I have more respect for the Perl developers I know.
To get really crazy, some languages like Python also have complex numbers, which are made up of two floating point numbers. One is real, and the other is imaginary. And if you don't recall from high school math, an imaginary number is one that is multiplied by I, where I is the square root of -1.
Yep. And you need that with engineering disciplines and a lot of other stuff. Now you can actually fake imaginary numbers in other languages too. Like you can make a type in C++ and do it, and there's probably something in the standard library by now.
Well, I'm sure you can. It's built into the Python language.
Yeah.
I mean, that would be a composite, but it is still built into the language. And when I was doing this research, I came across that, and I'm like, that is cool enough. I have to mention it.
There's some slick stuff in Python.
Someday in, maybe a couple of years when I have the free time, I'm going to learn Python because there's a lot of stuff I think is just awesome in it.
Yeah. So if any of this sounds familiar or interesting, and you want to learn more, we do have an episode just on numbers and computing and how intricate and nasty that actually is, because it sounds a lot easier than it really is under the hood.
Because actually that episode and the text episode were spawned from what this was supposed to be, which was a data structures episode, and it just kept getting bigger and bigger to the point where it was really like it was like expressing pi and just trying to do it base 10 in memory. Yeah. It wasn't ever going to end. Yeah. Since we've talked about floating point, the next thing I want to talk about are fixed point numbers. These are also rational numbers that may or may not have a fractional part. They have a fixed number of digits after the decimal. Some even have a fixed number before as well. They can improve performance and accuracy over floating points. Right. Sometimes. Yeah. Sometimes they make it worse. Yeah, because basically what you're doing with it depends on what you're doing with them. Yeah. Yeah. It really can vary a lot. Like for instance, you might keep track of dollars and cents with this because you know what level of precision you want after the decimal point, and you really don't care that it's off by 100th of a cent here. Like unless that's projected up to something, whatever. But basically what you're doing is this is the trick that we used to use a lot of times instead of fighting with floating point, which was represented as an integer and have a known number of digits before and after the decimal. That's exactly what so you can do your multiplication and then you just go, okay, boop, there's where the decimal is. Yep. They are most useful for representing base 2 and base 10 fractions. Gets quite a bit more complicated beyond that. The notation for representing the size of a fixed point number can be a bit confusing, as there are a couple of different ways to represent it depending on what is being controlled. In the Q number format, F is the number of bits in the fractional part, M is the number of integer or magnitude bits, and S is the sign bit. One way of representing them is the Q prefix, such as QF, or for example Q15, shows that there are F number of fractional bits, or 15. This does not denote the word length. It's usually assumed to be either 16 or 32. And it'll if you don't have all the values after that too, I mean it rounds. Yeah. It is what it is. Less ambiguous is the QM.F or Q1.30 as an example. This format is where the M is the magnitude or integer bit. Based on the number of bits in the M.F, the fact that there is a sign or not can be inferred. So Q1.30 denotes 1 integer bit and a 30 fractional bit. Therefore, to have 32 bits, you have an extra one for the sign. Yeah, and you can figure that out, but it's... And then the final way we're going to talk about in this episode, because trust me, there's a ton of ways to represent this, and it gets even more confusing the deeper you go down this rabbit hole. Yeah, because you start getting into scientific computing issues. So the other simple way of representing is the S:(M:(F), where you have the sign is the first bit, the magnitude or integer is the M, is represented the M, and the fraction is represented in the F. So in the Q1.30, it would be 1:1:30.
Right. And this is, if you've ever dealt with packed bits, this is that same kind of janky, weird way of storing things. It's just, it's a compression / performance optimization it's probably mostly dead in general purpose computing. You may run across it just on a real rare occasion. I mean, I haven't in a long time, and I deal with old stuff. I mean, this predates me, but you might occasionally run into it in scientific type applications or in documents. Like, like if you're looking at old government stuff or where somebody was showing how they were doing something in the 70s, you might see this sort of thing.
I just thought it was a bit interesting as another really not used primitive data type.
Yeah.
It was just sort of an interesting thing to bring up. Of course, these numbers have a more limited range, and like Will said, they're not really used these days.
Right. Because, usually you have the built-in types that are specific and everybody's taught about them.
Yeah.
And you do that.
So the next type we're going to talk about are the Booleans. These are logic types that can either be true or false, or null if it's nullable.
Yeah, and that's another weird thing as well, because, different languages treat this very differently. I know like in .NET, you have a Boolean value and it's a value. Whereas if you have a nullable Boolean, it's a object. It's heap allocated and it's wrapped.
Yeah.
Yeah. And the other neat thing is that instead of using a single bit, it's going to be a byte at a minimum.
Yeah, that's the interesting thing is because
you can't address a bit.
Yeah. True false dichotomy only requires one bit. But like you said, to be able to address it, you need the entire byte.
Right. Which is why a lot of times you'll see things like options for stuff, where there's a whole bunch of different bits. They may just say, okay, I'm going to take a double word or a quad word, and I'm going to put all those in there, and each one gets a bit position that toggles it on or off. And then I save that instead of a whole bunch of Boolean values that are mostly empty space. Because for like transmitting across like a slow internet connection or writing to disk or something along those lines, you want to shrink that down. That's not used as much now, but you'll see it when you deal with like operating system level things.
Some pretty low level stuff. I've seen that playing around with Linux.
Yeah.
Some languages treat Booleans as their own type, while others convert them into a number type.
Right. SQL, T-SQL does this. If you select from a table and it's got a bit field and you pull that back, you don't compare it to true or false. You say, is it equal to 1 or is it equal to 0? Unless your DBA is stupid, in which case is it equal to yes or is it equal to no because they made it a string.
Or you have a...
Sorry.
You've dealt with this. I understand.
At length.
You
Not
may have
at my current job, but at previous one. Now, it's bad enough that we have to say, okay, I'm going to take a byte and I really only need one bit of it. That's 7/8 of it that you're throwing away. Now, granted, that's a tiny amount of memory. But what they're doing is even worse because, okay, I'm going to store true or false in the database. Well, okay, I need 5 bytes. Oh, excuse me. Wait, it's Unicode. So you're storing a bit like in this massively inefficient way.
Oh, yeah.
I mean, the only way you could make it worse is like if you said, hey, I'm going to quote lines I'm going to put like the first sonnet from Hamlet in here if it's true, and the first one from Romeo and Juliet if it's false. Like that would make it worse. But other than that, you really can't do that.
So, I've been looking through a lot of stuff because, for audits, we have to have these, yes, I checked that, yes, I checked that kind of questions. Yeah. And they have to be stored as that. They can't be, if there is a date of doing something, then then the program assumes, yes, you checked it.
Right.
You actually physically have to have in the database a true false for yes, I checked it.
Yeah, and that should be a bit field.
Yeah, and
because otherwise it kills query performance too. Because doing string comparison is far slower than doing integer comparison.
What I'm getting at is outside of really odd requirements, like at a government level where it's legal requirements or industry regulatory requirements,
or where you're dealing with somebody where where the alcohol has affected their brain before their liver.
Yeah. What I'm getting at.
Sorry.
What I'm getting at is you're rarely going to be storing Boolean values because most of them can be inferred from, we have to say, did you do this? What date did you do this on?
Right.
Then by that date existing and not being null, then we can assume you did the thing.
Yeah.
And most places that is fine.
And that is most places that it works.
Outside
I'm jittery about it myself.
Yeah. Outside of the regulatory system, which is what I work in. So, that's fine.
And I deal with that with HIPAA data and those kind of things.
And
too.
I don't have a problem with it because of that. So a little bit about Boolean or binary arithmetic, and I'm probably going to state this later on, but we have an entire episode on this that I wrote as a filler episode, but after we recorded it, we decided it was good enough to be a regular episode. Boolean's either true or false. You have an output of true or false, 1 or 0, which may have a single input or multiple inputs of either true or false. These inputs go through logic gates to create the output. There are several different gates. The AND gate outputs true if both values are the same. So if they're both true, if they're both false.
Right.
The OR gate outputs true if either value is true. So if they're both true, it puts true. If one is true, it puts true. If both are false, it puts false.
Right. And that's if you're doing a binary, doing like straight up binary operations. I wanted to throw in that there's some languages that do some things that might be unexpected there.
Yeah.
But that's more of an expression tree evaluation thing, not a straight up bitwise.
Mm-hmm. The NOT gate outputs the opposite of what's inputted. If you put false into a NOT gate, it's going to change it to true, right. Vice versa. It's a bit flipper.
Yeah. Which really sounds like it ought to be like an insult that C-3PO would throw at somebody. And basically you combine sets of these to create logic circuits or to just create program logic in general.
In some languages, Booleans implicitly convert to other types like integers, but in other languages, you have to make that an explicit conversion.
Yeah, and personally, I would lean towards wanting that to be explicit.
Me too.
Because on and off is not the same as this is an integer. Mm-hmm. Like I can't add that to something.
I agree completely. And, just wanted to state that it was
it's possible. And it's a thing.
Finally, we're going to talk about characters. Now, a character or a car or char, however you want to pronounce it, I've heard it many ways, contains a single specialized unit, letter, digit, punctuation, the list goes on and on and on. It is the smallest addressable unit of memory. This is usually 8 bits, though.
Yeah, we have an episode on strings that gets into why that's...
Yeah.
Yeah.
A lot of standards require that the minimum unit of memory be 8 bits.
ASCII, for instance.
Yeah.
Well, yeah. It's so hard to pin this down because dealing with text data is so ugly. Mm-hmm. Just because of how many human languages there are and different notations for everything, and this kind of came a lot later than dealing just with straight up numeric values in computing, and as a result, the standards sort of had to converge a little bit. It was very U.S. centric for a long time, and then all of a sudden they go, "Hey, if I look around enough, there's like the rest of a planet here." And all of a sudden we had to deal with that.
Yeah.
And
exactly.
especially like the mid to late 90s, that stuff started hitting and you're like, oh, wait, we have international markets. We have all these, just NAFTA alone. Mm-hmm. All of a sudden you have Spanish characters coming in.
Exactly.
And, it will be, the smallest unit may be 8 bits, but when you're like, as far as it being addressable, the smallest unit for your purposes may not be 8 bits.
And we're going to talk about that in just a minute. So, the values within a character type precisely represent a code unit. And there are also, and these may be, like I said, letters, punctuation, things like that. There are also control characters.
Right. And that's things like your tab key, which is 9 in ASCII, or carriage. You may have composite ones of these too, like carriage return line feed, which is 10 and 13.
Mm-hmm. And these don't correspond with a specific symbol in natural language.
Right.
They're used for device instructions.
For instance, the beep key used to be 7. Well, I guess like it probably still is, but nobody does anything with it.
Yeah.
But I mean, that's from back in the old terminal days. So it's just you had to have certain commands for like, okay, now I know when I'm putting output to shift to the next line or to move over or to make a noise or do very simple things. And these are built into the way character streams are encoded now, even though modern times it's maybe not as useful as it once was.
Mm-hmm. And you're getting right into what we're about to talk about, which is there are different standards within the industry for encoding characters. A lot of what you've been talking about has been ASCII, or the American Standard Code for Information Interchange.
Right, which is it's an older code, sir, but it checks out.
It's a character encoding standard. It was the very first one commercially used, and it was originally developed from telegraph code. It encodes 128 characters into 7-bit code. What do they do with that last bit?
Well, I think aren't there special character ranges? I think it may vary between operating systems.
Yeah.
Like I don't see a lot with that. I know some of our, we've got some guys in the back that deal with a lot of encoding related issues with data streams coming in. And so they could probably talk at length.
So next is Unicode, an industry standard for electronic encoding of text in most writing systems.
Yeah, and emojis, and
it kind of encompasses.
It was designed to be expandable too, where they could do a lot of things with the address space in such a way that as new stuff is added, like I think they even have like a range for like Klingon or something. I mean,
I would not doubt that. Yeah,
as many nerds as there are, there's an RFC out there somewhere.
So.
In fact, if you guys can find that for us, we would love to hear about it. We're not going to go looking for it.
Yeah, that's true. But Probably. We would love to hear about it. And we will read your comment on the air and send you a water bottle if you send us that information. So Unicode has the Unicode Transformation Format, or what you may have heard is UTF, which is a version of Unicode encoding that can be fixed at various bit sizes. So UTF-8, UTF-16, 32, 64.
I don't know if you can do it at 64 or not.
They don't have that yet.
Yeah.
I threw that out there to be silly.
Yeah, I wouldn't be shocked if we get into it at some point.
Yeah.
Especially with advancing technology and things like, when you start getting more towards the AI type thing where those systems are developing their own languages for interchange.
Yeah.
Who knows what will happen with standards.
The size of a car or character varies depending on your encoding and the language you're using. For example, in C, a car is a data type that is the exact size of a byte, or is exactly 8 bits.
Right.
However, in other language, since Unicode requires 21 bits, a variable length encoding is used, such as UTF-8. What about strings?
Yeah, so a string at its simplest level is an array of characters.
Which would classify as a composite data type, not primitive.
Right. And we didn't even hit arrays on this because of...
That's going to be in the
that's in the composite episode,
yeah.
But it's a concept to understand but not talk about in this one. That said, they can be a little more complex. The way they're implemented varies between languages, between platforms. It varies a lot.
Like you said, the simplest form of a string is an array of characters, usually followed by a delimiting character to signify the end of a string, such as null terminated.
Right. That's one of the simple forms. Another simple form is what they call like a P string, like a Pascal string. So you start out with, hey, here's how many characters I'm allocating, now go. And those can actually be a little bit dangerous if they're coming in from user input, because somebody could cram a value in there that makes you jump past the end or makes you stop before the end, and then you're doing something with a stack and it pops out.
Yeah, I could see that being dangerous.
Yeah, so you'll see a bunch of different ways that these are done.
Yeah, you usually see these null terminated or the P strings in lower level languages like C, Pascal, assembly. They can also cause buffer overflows.
Yeah. There's a lot of very interesting things that can happen with these. And honestly, that the lower level representation is what the higher level representation is using. They're just protecting you.
Though I will say some higher level languages don't differentiate between strings and a character.
Right.
In them, a string with a length of 1 is a character.
Right.
Though some do contain both character arrays and a string type.
Yeah, and usually the reason these things are differentiated is it's a performance thing.
Mm.
Because if you only have one character, you don't need all that other crap about the length.
Exactly.
Or if you have, hey, here's an array of characters. It's this size, and I'm doing something with it. You don't necessarily need all the other stuff that goes with a string.
Exactly.
But in a lot of applications, you're not ever going to run into that. A string is a string, so they'd make it a string.
Mutability also becomes an issue with memory management, but we're not really going to delve into that because, like we've already said, this is more a composite data type. I just wanted to bring it up because we were already talking about characters. I knew the first thing that went through my head when we were talking about characters was, well, what about strings?
Yeah.
For more on strings and characters specifically, check out our episode, Let's Talk About Text.
Yep.
That was a fun episode. I remember doing that. Guys, in most languages, we're not talking about assembler here. We're talking about most of your higher level languages. Your primitive types will all be built in, or in other words, have native language support. Higher level languages will not allow you to alter the behavior of primitive types. So understanding how those behaviors work can make your code more efficient.
Right, because you can understand the underlying assumptions of the platform.
Exactly. And that pretty much wraps us up. Before we close everything out, Will, what do you have for us this week for Tricks of the Trade?
So for Tricks of the Trade this week, we kind of both wanted to jump in. So we want to talk about a phenomenon we both have been seeing a lot of lately. It just seems like it's on our radar. And that is the idea that when you see somebody else that is either being successful or helping other people be successful, that you have to tear them down. I find that to be very strange, but we've started noticing this a lot. I think some of it is just the general tension in the country right now.
Yeah, there's that. There's also a lot of jealousy. I think people seeing others being successful, and it's a recognition that if they put the effort in,
that they could be too.
Yeah.
And that they didn't. And so instead of confronting that,
like, it's not the people that don't have the ability. I mean, they all have the ability to be successful or to improve their situation in life. They just don't take that initiative. They don't put that effort in. And then when they see other people doing it, it reminds them that they're not doing that.
And I think some of it too is maturity. It's not realizing that, hey, look, I've got this one life and I have to live it. And I probably ought to do as much as I can with it. Instead, it's a thing of, oh, well, they just got it because it's easy. I don't know how many times I've heard that in the last, 4 or 5 months, especially. So-and-so had it easy because of whatever. And you hear about that about this person, and you're like, well, like their dad died when they were in high school. They got beat up every day on the playground. They, had all these horrible things happen to them. I've had somebody tell me that, my life was easy, and that's why I've been able to do what I've done. It's like, guys, I was chronically ill for 3 years. I missed 3 years of high school. I had 3 sinus surgeries in high school. I had a needle run up my nose in high school. I was bullied constantly. I was shy. I didn't fit in. That has no bearing on my success. It was just somebody looking from the outside going, oh, you had it easy.
Well, it's something that I've talked to some of our other guests that we've had on the show about, is they look at people who have made it.
Yeah.
And they see the success and they're like, they make it look easy because they're not showing all the failures.
Right. Well, and the other thing is you get to success because you have figured out how to avoid the failure and how to do that as really part of your process.
We do that with this show.
Yeah.
I mean, how much of the episodes never make it on the air?
Yeah.
And don't even make it to the bloopers reel or how many episodes, especially when we first started out, how many episodes did we record and never published?
Yeah. There were 3 or 4 of them, it seems like. Yeah. And then there were large swaths of some episodes where we're like, wow, that sucked. Mm-hmm. Start over at this point, go from there. And that's what you do. And people don't see that. And so they assume that, okay, because I'm seeing the finished product and it looks simple and I don't see the evidence of the work, that means the work didn't happen.
Yeah. It's interesting. We just had the episode with the Junior Developer Toolbox crew.
Yeah.
And we've had all of them on. Jason has been our audio guy since probably episode 15 or 16. and helping me out with everything, but I'd do the editing and then send it to him for post-production.
Right.
He said, I think he stated at one point in the episode, wow, I didn't realize how much work you guys put into this, because he's like, I just thought you just talked that clear and that natural.
Yeah.
It's like, no, we screw up, we fumble, we re-say things all the time.
Yeah. And I don't know. The thing that's really galling to me is if somebody sees that, okay, we have a finished product that's good. Like, we've spent the time to get to that point, and their only reaction is, well, I'm going to try to make you feel bad. I'm going to say that this is clickbait for retards on Facebook. Like, this happened today, and this is like the second time this same person has done this. And it's, for one thing, it really says something about where that person's coming from, right? Yeah. Like, it doesn't affect us that much. I mean, it irritates me, but at the end of the day, I'm doing pretty good.
Yeah.
And that person clearly isn't, because they have enough time to be on Facebook trying to troll. But I wonder about, if you're looking around your life and you start noticing that, hey, this is the way I'm reacting to people, you might need to figure out where that's coming from, because this is not going anywhere good. Like, you will still be where you are 10 years from now.
Yes.
If you're doing that. And that's unimaginable suffering, because you're not in a happy place when you're doing this. It's not like, you're self-assured and you're strong and everything's going well, because now I'm going to get on Facebook and troll. It's like, no, I'm angry, I'm bitter, I'm whatever, and now I'm going to get on Facebook and troll. And you're doing things in a way that makes sure that you're going to still be doing that. I don't know, man. It's messed up. That's all I got.
Stand by for Titanfall.
If you have a question or comment, please email us at neckbeards@CompleteDeveloperPodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed through Creative Commons. The intro music for IoTs is Hillbilly Hip Hop by Jason Belcher. For references, show notes, and to sign up for weekly emails with extra tips and insights, be sure to check out the website at CompleteDeveloperPodcast.com. You can also follow us on Twitter at CompleteDevPod and like our page on Facebook to keep up with news about the show. Look for us each week on Facebook Live before we record each episode. Thanks for listening. See you next time.